We have already discussed up to work power energy topic, and work energy theorem is already discussed, and then we discussed the conservation of mechanical energy. Now regarding conservation of mechanical energy, we have already discussed two form of the mechanical energies. One is kinetic energy and the other one is potential energy. Okay, so we have little bit concept about the kinetic energy and potential energy. Now we will discuss the work done under variable force. Work done, we will choose a variable force which is the force of elasticity or force given by a spring when it is stretched or it is compressed. That force is calculated by Hooke's law. Suppose there is a spring and a block is attached with that object, and the other side of the spring is connected to a rigid wall. Now if we consider that this block is on a frictionless surface, then if you pull the block to this side, then there will be a force produced in the opposite side. That force is called the elastic force or the restoring force. This is coming from the elastic behavior of the spring, which will try to bring the spring back to its natural length. Okay, suppose spring is of length 10 centimeter. You pull it and such that its new length will become 11 centimeter. Then its stretching will be 1 centimeter. Then if you stretch, the elastic force will act in the opposite direction of the stretching and it will try to bring it back to the 10 centimeter. That force is called the elastic force. Now this force is the force applied by you. So write it as applied force. Okay. Now the spring is displaced along this direction. Spring is elongated along this direction because mass is displaced from this position to this one, suppose by x. Then increase in length of the spring is x. Okay. Now the elastic force acts in opposite direction. So I can write F elastic, or sometimes this symbol is also written Fr. That is F restoring. Restoring means it will try to restore the spring to its natural length. Okay. These two lights switch on. See, Fr. This is F. Okay. See. So we apply a force F to pull it. Leave. See. We apply a force F to pull the mass on this side. Now if you try to pull, then the spring will elongate from its natural length. So once the spring will elongate from its natural length, the elastic force or the restoring force acts on the block, and it is exerted by the spring to bring the spring back to its natural length. Okay, such that the extension will decrease. The same phenomena occurs if instead of elongating you are applying a compressive force. So if it is compressed, then restoring force will try to move it in the outward direction such that its length will remain same. Now as long as this mass is in equilibrium, means when you are changing, not at that time, but after the complete change, if you suddenly stop, means the equilibrium, then Fr and F, this should be equal. So we always denote this restoring force or the elastic force by the value of the applied force. Okay, so write down. In equilibrium condition, equilibrium means net force 0. The magnitude of elastic force is equal to the magnitude of applied force, So there is no need to denote it by F suffix R, you can directly write F. Okay, now, so by taking the elastic force as F, then I can write F is proportional to displacement, that is elongation or compression. F is proportional to the elongation or compression, this restoring force. Then I can write F proportional to X. So as the elongation or the compression increases, the elastic force or the restoring force will also increase. So this is a directly proportional relation. This relation was given by Robert Hooke, and as a result it is termed as Hooke's law. Okay, now there should be some proportionality constant. That proportionality constant is taken as K, called the spring constant or the force constant of the spring. So F can be written as K into X. Now see one thing, in which direction restoring force acts? Along this, and displacement is in the opposite direction, so there should be a minus sign. Whether it is compression or whether it is elongation, in either cases restoring force or the elastic force is against the displacement, because it will try to decrease or increase the length such that the spring can be restored to its natural length. So that is always opposite to X. So that's why F equal to minus K into X. That is the restoring force. So if I am asking you what is the magnitude of this restoring force, just only Kx. But minus sign comes due to the direction. Clear? Now, I want to calculate the work done by this restoring force. Now see, in this case, initially the body is here. Now the body is here because it is stretched. Then what is the work done by the restoring force? The force is given, its displacement is X. So what is work done? Force into, that is minus K X square. No. See, you can multiply force and displacement directly to calculate work done only when the force is a constant force. But here the force is not constant. See, when displacement X is 0, what is the magnitude of this force? 0. When X equal to 1, this will be K. When X equal to 2, magnitude will become 2K. X equal to 3, magnitude will be 3K. So the magnitude of the force is continuously changing. So this is an example of variable force. Then for each position of displacement, magnitude of force is not same. So we have to integrate. Clear? So whenever there is a force, force is not constant containing the variable term. Here it is a function of displacement. So we have to integrate. Clear? Now, so then we can consider that for a very small displacement, work done is dW. That can be written as F into dx. Very small displacement is dx, and for that this force is doing a work dW. Then dW can be written as F into dx. Then I will substitute this value of F here to calculate the total work done. So total work done W equal to integral minus K will be there, minus K is a constant, integral x dx. Suppose initial elongation is nothing, so 0, final elongation is up to x. So you can write this one is minus k x square by 2, that is minus half k x square. So this is the work done by the elastic force of a spring, minus half k x square. Okay, minus half k x square. Now think about a similar situation. When an object is moving up, gravitational force is downward and displacement of the object is upward. So gravitational force and displacement angle between them is 180 degree. In that case, work done by gravitational force is negative, minus mgh. Okay, now in this case work done is also negative by the elastic force of the spring. Now see, whenever the body is moving up like this, gravitational force is doing negative work, then some energy is stored in this object. Which energy? Potential energy. So because we are considering it is moving with constant speed. Constant speed means that other day we discussed, constant speed means kinetic energy will not change. So it is gaining height. So gravitational force is doing negative work, means potential energy will stored in the particle. Now in this case, elastic force is doing negative work, so potential energy will stored in which object? In the spring. So that's why if a spring is compressed, suppose elastic potential energy is stored in the spring because it is deformed. Now you release, it will suddenly jump off. So how it gets the kinetic energy? Because due to compression, some elastic potential energy is stored in the spring, and that's why when you release this elastic potential energy tries to convert into kinetic energy, and that's why the spring jumps off. Clear? So think about the situation. If a force is doing negative work, then potential energy will be stored in the object or in the system. Clear? Gravitational force is doing negative work, then gravitational potential energy is stored in the mass. That's why it is moving upward. Similarly, spring force or the elastic force is doing negative work. That's why potential energy is stored in the spring. Now, if you release the spring, this force is absent, then this elastic potential energy will be converted to the kinetic energy and spring can move to come back to its natural length. Clear? Now, suppose there are two conditions. One mass is here, another mass is here. In which situation potential energy of this mass is less? In this condition. So when it is at a lower height, then potential energy will be minimum, gravitational potential energy. Similarly for the spring, when it is at its natural length, then its elastic potential energy will be minimum, that is 0. If it is either increased, elongated or compressed, in either situation potential energy will be more, and that potential energy is called the elastic potential energy. That's why there are two terms of potential energy that is defined. Two types of potential energy is defined. One is how potential energy you can define? It is the energy due to the position or configuration of an object. Suppose a mass is here, the same mass is taken here, so the position is changed in the gravitational field, so gravitational potential energy will be stored in the mass. Similarly, in case of a spring, if you compress it or stretch it, its configuration will change. So due to configuration change, there is potential energy, and that is the elastic potential energy. So you have already studied two types of potential energy which comes due to the change in position. One is gravitational potential energy, another you are reading in class 12, electrostatic potential energy. That is also due to the change in position, because if you are going from one position to another position, electric potential will change. As a result, electric potential energy will also change. Two types of potential energy due to change in position, and one type of potential energy you have discussed, that is the elastic force. The elastic potential energy, that is coming due to the change in configuration. Clear? Now, then this work done by the elastic force is negative, then potential energy stored in the spring will be positive. So we can write the change in potential energy U equal to minus of W, that is the potential energy stored. It will be the negative of work done. So it will be just plus half K x square, plus half K x square. U equal to minus W. So if work done is negative, potential energy will be stored, that is denoted by positive sign. That's why it is half K x square. Okay. Now, is it clear? So we will discuss a problem. This force is given. Force is given as A plus Bx. A plus Bx. Okay. Then find the work done by the force in displacing the particle it is the force acting on some particle. Find the force in displacing the particle from x equal to 0 to x equal to 5. x equal to 2 to x equal to 5. All units are given in SI, means this 5 is meter, force is given in Newton, all this. So final answer will be in work done, that is joule. So you have to go through the formula W equal to integral F dx directly. This one, in displacing the particle from x equal to 0 to x equal to 5. See, W equal to integral f dx. F is this one, a plus bx into dx, 0 to 5. Then first term is a integral dx, 0 to 5. Second term will be b integral 0 to 5 x dx. So integration of dx will be x. So it will be a into 5 minus 0. Integration of x dx will be x square by 2. So it will be b by 2 into x square, means 5 square minus 0 square. So this one will be 5a plus 25 by 2b. Since it is given all the quantities are in SI unit, so this unit will be joule. So this is the answer. 5a plus 25 by 2b. Just simple integrating the function of force with respect to displacement f dx, and then you will get the result of the work done. The force is one dimensional because it depends only on x. If that is a two dimensional force, then how to calculate the work done under variable force? Okay, see, I will take one example and demonstrate this. Suppose force is given as F equal to x square I cap plus minus yj cap. This is the force. Write down. This force is acting on a particle. This force is acting on a particle and displace it from point P this point. Displace it from point P to point Q. The coordinates of point P and Q are given. Coordinates of P is 2, 1. Coordinates of Q is -3 plus -3, +8. So you can construct the diagram that in a xy plane there are 2 points P and Q. So joining them you will get a straight line. That is your displacement. But force is given as a variable in the xy plane. Then how to proceed? First we have to find out the displacement as a vector. Now normally we are eager to write the position vector as r equal to xi cap plus yj cap. Now what will be the elemental position vector or the differential position vector? I can write here dr, that is equal to dxi cap, similarly dy j cap, because if x is very small, dx, y is also very small, then their resultant d, which one? This part r. Generally we write position vector r equal to xi cap plus yj cap. Now if I say that position vector is not that much long, so x is very small, so we can write it dx, we can write y as dy, then we write r as dr. Okay. So if all the parts are very small, that is small displacement called differential element or differential displacement. Now similar to f into dx, now what we have to do? F into dr, but that should be a dot product, because on the other day I discussed that work done is defined by f dot s. So now you have to calculate f dot dr. So first write dw. dw will be equal to f dot dr. Okay, f dot dr. Then just calculate the dot product. What it will give? The coefficient of I cap is x square. Here coefficient of I cap is dx. So ax bx. So it will be x square dx. If there are two vectors and we are calculating the dot product, so I cap's coefficient is multiplied ax bx. Next term will be ay by. So ay is minus y. by is dy, so it will be minus y dy. Z term is absent, so this will be the dw in the scalar form. Okay, after doing the dot product, remaining part is a scalar. So previously there is only one component, that is x, so I write f dx. Here x and y both components are there, so we have to do this dot product to find the work done as a scalar function. Clear? Now we want to calculate the entire work done. So we have to do the integration. So there will be two separate integration, one for x and other for y. Now, what is the particle's initial position is P, final position is Q. So initial x coordinate is 2, final x coordinate is -3. So write it 2 to -3. Initial y coordinate is 1, final y coordinate is 8. So 1 to 8. Now calculate the integration and find the value. So if I integrate this term, so w will be equal to this one, x squared dx. Its integration will be x to the power 3 by 3. Limit is given 2 to -3, minus y square by 2. Limit is given 1 to 8. So now we can write here, it will be 1 by 3 into -2 whole cube, -2 whole cube, -3 whole cube. -3 whole cube means -27 minus 8. 2 cube is 8, minus 1 by 2 is there. 8 square means 64 minus 2 square, that is, sorry, no, 1 square, that is 1. 1 by 3 is there, upper limit is -3. So x equal to -3 first put, it will be -27, then lower limit 2, that's why -8. Similarly here, half will be outside. 8 square 64 minus 1. 1 square is 1. So you can write the result, that is -27 minus 8. What is that? 27 plus 8, that is 35. So it will be minus 35 by 3 minus 63 by 2. Whatever it comes, that unit will be joule. Write down. A block of mass m, small m, a block of mass small m is falling from a height small h over a massless plate, over a massless plate, which is mounted over a spring, which is mounted over a spring. Okay, whose force constant is K, whose force constant is K. Okay, now mounted over a spring whose force constant is K means the lower end of the spring is on the ground. From the beginning, a block of mass small m is dropped or is falling from a height small h over a massless plate mounted over a spring, mounted over a spring of force constant K. If the ball does not rebound after striking the plate, if the ball does not rebound after striking the plate, then calculate the maximum displacement, maximum compression, then calculate the maximum compression of the spring. Calculate the maximum compression of the spring. First, whenever this type of problem is given, first you have to draw a rough diagram. What is going on, then it will be clear. It is on the ground and the ball is falling from this height. It has mass m. This height is specified, that is h. You have to find out the maximum compression. The spring constant is given K. This is the situation. Now see, when the ball strikes the plate, it will strike with certain velocity, then it will exert a force on the block, so the spring will compress and it will come down. But as the spring compresses, another force generates in the upward direction to counter the weight, that is elastic force, because elastic force tries to oppose the movement and to bring the spring back to its natural length. Now what happens, due to this force, it will compress, suppose up to this, and then elastic force will be that much when it can balance the mg, then further compression will not occur. Then that is called the maximum compression. That is called the maximum compression, because mg is fixed, mg is striking. So as the mg is striked, this spring is compressed, and then due to compression, elastic force gradually increases from its zero value. So when this increasing value of the elastic force will be equal to the weight, then it cannot compress further, means at that moment the compression is maximum. So that maximum compression I have to calculate. But remember, in this case, when the mass strikes on this, it is suddenly striking, means it is an impulsive force, and characters of impulsive force are very notorious. We cannot calculate properly for the impulsive forces. Okay, so we will use not the force technique to calculate the maximum displacement such that velocity will be zero, because you have learned the equations in kinematics, that is v square equal to u square plus 2as. For retardation it will be v square equal to u square minus 2as. Now we can consider that final velocity will be zero, but in that case we cannot use this equation, because in kinematics the retardation or acceleration used there is constant, but here acceleration on retardation is not constant, because mg is constant but the spring force, that is variable force, so it will produce variable retardation, and those equations are not valid for variable retardation, that is only valid for constant acceleration or constant retardation. Then we cannot solve this problem by directly applying Newton's law, so we learn work per energy and we use the energy technique or the conservation of energy to solve this problem without hampering, without knowing anything about the variable nature of acceleration and all these things. I can solve the problem. How? See, suppose maximum compression of this spring is up to here, so this mass will come up to which point? This point. I will draw it here. Spring will be so compressed now, the mass will come with this platform here. Let us consider this maximum compression is x. Maximum compression is considered as x. So what will be the total height by which the mass is falling? mg h. So I can mg h plus x, not mg h. mg h is up to this. Further, how much it is coming down? X. So what is the total distance falling by the mass? H plus x. So what is the loss in gravitational potential energy? This is the loss in gravitational potential energy because it is coming down. So in the upward position gravitational potential energy is more. Now as it is coming down gravitational potential energy is decreased. So this is the decrease in gravitational potential energy. Achha. Is there any dissipative force like friction or anything? No. So total mechanical energy must remain conserved. Now this change in potential, gravitational potential energy is converted to which energy? Loss in gravitational potential energy, there is a loss. That loss is converted to the kinetic energy. See, when it is falling, you release this mass. It is coming down, so its gravitational potential energy decreases. So which energy increases? Kinetic energy, because it is falling with acceleration. So velocity increases, kinetic energy increases. But here, when it is compressed by maximum amount, it is coming momentarily at rest. So what will be kinetic energy? But energy cannot completely lost or destroyed. Then in which form it is converted? Compressed part. This energy is stored. So loss in gravitational potential energy is stored as elastic potential energy of the spring. How much it is compressed? By an amount? Now spring compression. Spring compression is only by x. So elastic potential energy stored in the spring will be half k x square that we earlier derived. So equate this with half k x square. Equation is complete. No more equation is required. Because it is falling and compressing the spring up to maximum amount x. Then total height falling by the stone is h plus x. Then its loss in gravitational potential energy will be mg into h plus x. Now at the maximum compression, the mass is momentarily at rest, so its velocity is 0. So there is no kinetic energy. So entire loss in gravitational potential energy is stored as elastic potential energy inside the spring. So elastic potential energy for the spring due to compression by an amount x will be half k x square. So we equate these two because energy is conserved. Clear? Now from this equation you have to find the maximum value of x. Now if I rearrange this equation, I can write this as kx square equal to 2mgh plus 2mgx. Then you can write kx square minus 2mgx minus 2mgh, that is equal to 0. Okay. Now how many values of x can be obtained from this? 2 values. By Sridharacharya's method you can solve. You know Sridharacharya's method to find the values of the quadratic equation. Then you will get 2 values. One value is with minus, another value is with plus. The maximum value then you have to choose for your answer. Suppose 2 values are coming. One is with plus, another is with minus. So which one is the maximum compression? The value with plus. So take the larger value and that is the maximum compression. And if the value of mass g and h, all these are given in numerical as a numerical value. Good morning, good morning. So if they are coming as the numerical value, then you can find and solve the value. And if 2 values will come, then check which one is maximum value. Suppose it is coming minus 2 and plus 4, then obviously plus 4 is your answer. Maximum compression. Suppose it is coming 2 and 6, then 6 is the maximum compression, 2 cannot be the maximum compression. So if this type of problems come, don't get panic. First try to, if you find the acceleration is variable, then you cannot use the equations of kinematics directly, because those equations are valid for constant acceleration. Then immediately try to solve the problem by using energy equation or work done, because that deals with the scalar quantity and even valid for variable forces or variable accelerations, where the normal technique of kinematics will not work. This one is a bypass technique and can solve the problem easily. Okay, so again recap what we are doing. It is released from here, so it is going down, it is compressing the spring up to this. So maximum height that it can come down is h plus x. So loss in gravitational potential energy due to this is mg into h plus x. Now this portion velocity is 0, I write it, velocity is 0 at this portion, so that is the maximum compression. Then entire potential energy loss due to gravity is converted to elastic potential energy of the compressed spring. Then elastic potential energy half kx square, equate these two, because total mechanical energy is conserved. So equate these two and find the value, larger value of x. Clear? Solve করব না এমনি বসিয়ে দিতে পারি। Sridhar Acharya's method, who remembers minus b plus minus root over of b square minus 4ac by 2a. See this one, ax square plus bx plus c, if 0, then value of x will be minus b plus minus root over of b square minus 4ac, called the discriminant, by 2a. Markers are not working properly. See, this is the formula for solving the quadratic equation, minus b plus minus root over of b square minus 4ac by 2a. This is called the Sridhar Acharya's formula. Okay, now identify from it what is a in this equation, k. What is b? Minus 2 mg. What is c? Minus 2 mg h. Just put. If you try to calculate in this format, then you can directly put. This is the general formula that I have written. According to that, compare with x square, x and constant term and find the coefficient ABC and then put in this equation, Sridhar Acharya's formula. Okay. So the physics part of the problem is this one. Once you write this equation, the physics part is complete. Rest of the thing are to solve by using mathematical techniques, whatever you know. If there are numerical values are given, it may comes as a middle term factor, then you factorize and find the values. That is a part of mathematics. The physics portion is that how to apply the conservation of energy for this problem. That is, there is a loss in gravitational potential energy, so total energy cannot be destroyed, so this must be converted into some other form. Kinetic energy is not there because at the maximum compression velocity is 0, so kinetic energy is 0, so it is converted to the elastic potential energy of the spring, and these two should be equal because otherwise conservation of total energy will be violated. So that is the main concept to solve this problem. Okay. Now see, now we will discuss another part of the work per energy topic, which is also related to the circular motion or the motion along a curved path. So work per energy is also required to solve those problems. So we will see one such type of problem. Check. Let us consider this is a hemisphere and a stone is there, just a small block, not stone exactly, small block at the top of the hemisphere. There is a small block, very small block at the top of the hemisphere. Okay. Now you are giving a small push, just minimum, just it is displaced. There is no friction and it is falling. Tell me whether it is falling exactly over the hemisphere and come to this point, or after some point it will move outside, not touching the hemisphere anymore. It will release from the hemispherical surface. It will detach from the hemispherical surface after falling certain distance. Why? Why it will leave the hemispherical surface? Just only this question is not for any calculation, only the conceptual question. Suppose 4 options are given that why it is leaving the hemispherical surface, and 4 options are given. Here I am not giving the option, I directly ask you why it is leaving the hemispherical surface. No calculation, nothing is required. Only you have to think about the property of the circular motion. Again, what? It is tangential force. Okay, fine. Who is giving tangential force? Your answer is correct. It is due to a tangential force, that's why it is leaving the surface. Because if it is only centripetal force, then it cannot leave the surface. There is some tangential force, of course, due to which the magnitude of the speed increases. Since the magnitude of the speed increases, magnitude of the velocity vector increases, means speed increases. Gives this force because acceleration is effect, force is cause. So force produces this effect that there is tangential acceleration, and due to tangential acceleration the speed will increase, and due to increased speed centripetal force is not capable of holding it in the circular track and it will leave the surface. That is the result. So if there are options given, which force, due to which force it leaves the surface, suppose given normal reaction is there, suppose given mg is there, suppose centripetal force is there, so out of that you have to choose the option mg, that is weight. So weight gives us this, gives the block this force due in a tangential component is there, due to which the tangential acceleration will come, and as a result the speed will change. Since speed is increased, centripetal force is not capable of holding it over the circular path, so it will leave the surface. So always think before solving on anything what is asked and what is the physics behind it. The physics behind it is presence of a tangential force which can create this detachment from the surface. Clear? No calculation is required for this problem. Achha. One more thing that I will tell you, if someone asks you this circle has a radius r, this hemisphere has a radius r, then it is initially at this height. Now suppose at this height it is released from the surface, then what will be that distance after which it released from the surface? Remember this one, its proof will not come, it is r by 3. You have to remember this one, because proof is not at the NEET level, that is a question of the JEE. After falling a height of r by 3, it will be detached from the surface. Now we can prove it, but it is not required at this moment. If I do that proof, you will, all of you will sleep. Stay properly, don't sit like this. Sit properly, you don't sit like this. After some time you will definitely sleep. See, so you have to remember this one, that after falling through a height of r by 3, it will leave the surface, because in that case the velocity will be speed will be increased that much that it will detach from the surface, normal reaction will be 0 and it is coming outside. Now there is another part of this. Suppose a cyclist is taking a turn around a road. I consider first the road is exactly horizontal. Just suppose he is coming like this and he wants to take a turn. Road has some friction. Now if I draw the diagram a little bit amount like this, at any moment the cyclist is here. Suppose it is taken as a mass. So what are the forces acting on the cyclist right now? mg, downward, normal reaction force from the ground, upward. In which direction he is taking a turn? Turning radius is here. Suppose radius is r. It is taking a turn in a radius of r. Then consider from the frame of the cyclist, that is that an inertial frame or non-inertial frame? The frame of the cyclist non-inertial, because cyclist is taking a turn means he is suffering centripetal acceleration. So his frame is accelerated. So accelerated frame is non-inertial. So in non-inertial frame he will find a force acting on him. That force is called centrifugal force. What will be its magnitude? Same as that of the centripetal force, that is mv square by r. So on the cyclist there is a force in the outward direction, that will be mv square by r as felt by the cyclist in the non-inertial frame when he is on the cycle. Clear? Whenever we are inside a car is taking a turn, we are feeling a force outside. So that cyclist will feel this force mv square by r, but he cannot say a origin of that force, so that is pseudo force. These three forces. But now think about it. Due to that mv square by r, cycle will skid outside and the man will fall. So which prevents the cycle from skidding? Friction. Good. If friction will prevent the cyclist from skidding, then which direction friction should act? Inward, such that it can balance mv square by r. Due to this force, cyclist had a tendency to skid, or cycle has a tendency to skid outside, move outside. Then friction should be there to stop its outward movement such that it will not skid. Clear? Now, from the equilibrium of the cyclist, if cyclist is not falling, then he is in equilibrium. So cyclist will say that net force on my body is 0. So he will write the equation as F equal to mv square by r F equal to mv square by r, and for normal reaction he will write mg. Now if the coefficient of friction is given, then we can write F equal to mu n. So just put the value of F and n in this equation. It will be mv square by r equal to mu mg. So m will cancel. So v will be equal to root over of mu rg. So this is the maximum velocity with which the cyclist can negotiate a turn. If the road is horizontal and cyclist when passing over the road remains his cycle horizontal. Clear? If it try to take a turn with more velocity, then friction cannot stop the centrifugal force, because if it is taking a turn with more velocity, then due to more velocity this force mv square by r will increase, but friction cannot increase beyond its limiting value. Then friction cannot stop, and as a result he will move outside and fall. That is the condition. Okay. Now, a very dangerous situation can arise if the road is horizontal but there is no friction. In that case, what he will do? Road is horizontal but there is no friction. How can he negotiate a turn? See, like this, he cannot negotiate a turn because friction is not there. So if it try to take turn, then there is no friction, so it will definitely fall. So how he can negotiate a turn in a horizontal frictionless road? How? Fall from the circle. Then he has to tilt the circle towards the turn and take this. He cannot stay like this and take the turn. He has to tilt itself for taking the turn. Now, what is changed if he is tilting? The normal reaction force will only change the direction. It is like now this one. See, Now the situation is that if I draw this like this is the cycle part, mg is downward, there is this normal reaction force N. Now normal reaction has two components. One component is there, so let us consider he tilted himself at an angle theta with respect to the normal. Then this component of normal reaction will be N cos theta, this component of normal reaction will be, and there is this centrifugal force. So now in the rod having friction stops this mv square by r. But if this is frictionless, there will be no component, so the man himself has to tilt the cycle such that one component of normal reaction is behaving like friction, n sin theta. Then if this n sin theta is equal to this one, the man can negotiate the turn, otherwise not possible. Okay, so he will bend the cycle in this way, then in the direction of friction, now there is no friction, so in the inward direction some component of force can be generated, and that can be generated by component of normal reaction force. Okay, so now he will write this equation as mv square by r equal to n sin theta and mg equal to n cos theta. Divide these two, you will get v square by rg, that is equal to tan theta. So from that, if you know v, r and g, you can find the value of the angle at which the man has to tilt his cycle. Okay, and even you can find the value of this v by taking root over of rg tan theta. So if the theta is given, that means at how much angle you have to tilt, then you can find the maximum velocity. If this velocity you are taking more than that, then even in this case you will fall. So you have to take this much velocity or less than that. You cannot cross that velocity. If you cross that maximum velocity, you will fall. Previously, friction prevents you from falling. Now a component of normal reaction prevents you from falling. These formulas you have to remember, that if some question comes regarding that this friction is there or friction is not there, how many angles you have to tilt when maximum velocity is given, so you have to calculate from these formulas directly. And this is a very easy problem if you know the value of other quantities and you have to ask to find the maximum velocity or the angle of tilting, that things you have to be calculated. Okay, so if you forget these formulas, then you have to do all the calculations and derive the formula and then solve the problem. That much time is not available in the exam, so you have to remember all these things. Now, if the road has friction and even in that case the cyclist is bending, then he can increase his velocity of taking a turn, because friction is there to prevent centrifugal force, plus he is additionally tilting it inclined like this. So in that case normal reactions component will be there, friction will be there, so two components are there to prevent the centrifugal force, so the velocity can be increased. That same technique is used in the bike racing. Whenever bike racers are taking a turn, near the turn they almost tilt himself like this, such that this n sin theta portion will increase, because if he is inclined more, then theta will increase, and if theta increases, sin theta will increase. Theta increases, sin theta, sin 0 is 0, sin maximum is 90. So if theta is increasing, sin theta is also increasing. So the increased value of normal reaction is added with friction. As a result, he can take the turn with large speed. It will not fall. So that's why biker near the turning, they incline almost like this and they can take the turn. Okay. Now, if there is a four-wheeler or three-wheeler or a multi-wheeler, then how to negotiate the turn with a high speed? Now you cannot say I am inside a car and I can incline the car like this. I can tilt the car like this. It is not possible. For two-wheeler it is possible that suddenly you are taking a turn and that moment you bend yourself. But for four-wheeler, for train, can driver of the train tilt the train? It is not possible. So that's why road near the turn is inclined, such that normal reaction will be like this, and one component of normal reaction comes to prevent the centrifugal force. That is called the banking of road. Whenever there is a curve in a rail line, you will find that train is inclined. It is not that there is any defect in the line. It is due to that with a very high speed the train can take a turn safely, because if it is like horizontal, then train will be derailed. So this should be like this, and this inclination is there in the road. Even in highway, if there is a turn, then during the turning the highway looks like this. So the car will come like this and it will take a turn in this way, such that their surface is like this, car is like this, so it has a normal reaction along this. So this normal reaction can be splitted into two components. Due to high velocity, centrifugal force is there, and one component of normal reaction is trying to stop it. So that's why the roads are banked near the curve. Clear? Hill roads near the turning, they are banked too much. During the hairpin bending, they turn too much. So due to this banking effect, to produce this banking effect, the roads are inclined in one way inside the turn. Okay. Now, how to find the maximum velocity and minimum velocity regarding that turning? Now I will derive both the part, but minimum velocity is not required for a car. Only maximum speed limit is required for the car or train, anything. Minimum velocity is required in some problems. I will mention that problem. Let us consider this is the incline, at an angle theta. Now you cannot see. Anyone go to that and bring another marker, black marker or blue marker, anyone. None of the markers are working well. You want to take a break, but only 5 to 10 minutes, not more than that. So now we will construct an inclined surface like this. Now this one is actually a cross section of a banked road. Means the road nearby you, whenever car is taking a turn, is like this. There is a sloping, and suppose you cut it from one side and look to this cross section. So if you look to this cross section, it appears like an inclined plane upward, but the cars how are moving? They are not moving like this, they are moving like this. Okay, because over the incline they are moving over the incline, not along the incline upward. So you can construct the structure of a back portion of the car like this. This is the situation that looks like. Suppose the car is moving from this side into this and inside. Okay, now in this situation I want to draw all the forces on the car. See, I consider the non-inertial frame, that is the frame of the car. First force is mg. Okay, downward there is a normal reaction force. Upward I consider the car is negotiating the turn with a very high velocity, maximum velocity. Then in which direction centrifugal force act? See, in which direction? Downward. Centrifugal. Upward along the incline or downward along the incline? Centrifugal force acting on the car along the incline upward or along the incline downward? Neither along the incline upward nor along the incline downward. Why? See, suppose this one is the banked road, car is moving like this. So what is the turning center? Here. You can consider that it is over a banked road and moving in a circle like this. So what will be the radius of that circle? Along the same plane. It cannot be downward, it cannot be upward. So center is here. So centripetal force is towards center. So the centrifugal force is away from the center. So from the position of the car, it is going outside. See why I am saying this one. This one. This is the center. Because I am drawing a cross section of the road. The car is going around this road. This is an inclined turn. Okay. Now this is the center. So it is directed opposite to that. Just think about it. This road is 3D surface. This one. Car is going over this. So the center of the circle is here. So it is here. So centrifugal force is directed opposite to that in center. Okay. First think about it. If this is the incline, curved road, just it is a 3D diagram, think of it. Like this. So the car will move like this. So it is moving in a circle whose radius circle is in this plane, not in this plane. It is like this. So center of the circle is here. So centrifugal force will be in the opposite direction. So this is the direction of this centrifugal force. mv square by r, where r is this one up to center. So consider this one as a 3D visualization. You have to visualize in 3D. Okay. Now, in which direction friction acts? In the direction of tendency to skid. If it is a high velocity, then direction of tendency to skid is upward. Then in which direction friction acts? That is along the incline, because you cannot draw friction directly opposite to this force, because friction is a contact force. It will act along the contact line. Contact line is this one. So draw this friction here. It is denoted as F. Now all the forces are drawn. There is no more force acting on this car as observed from the non-inertial frame. One is mg, vertically downward. One is n, perpendicular to the incline, upward. One is friction, along the incline, downward. One is mv square by r, that is centrifugal force, opposite to the, away from the center of the turning. Center of the turning is there, not at the bottom, okay, and it is in the opposite direction. Now F and N, they are already perpendicular, so we will not try to split them into components. Clear? F and N, they are already perpendicular to each other. Now the other two forces has to be splitted into components. I will resolve those two forces only. One is mg. Now if this angle is theta, you can construct one component of mg here. What will be its value? Mg cos theta. And what is the other component along the direction of friction? That is mg sin theta. Similarly, I will split mv square by r. First complete this component of mg. Okay. Now component of mv square by r. See, one component of mv square by r should be along the incline upward. Another component should be perpendicular to the incline downward. This angle is theta. So this component is mv square by r cos theta, and this component will be mv square by r sin theta. Now all the force diagram is complete. Free body diagram complete. This one theta, so that one should be theta, corresponding angle. Then this component is mv square by r cos theta, and perpendicular downward component is mv square by r sin theta for the centrifugal force. So we resolve centrifugal force and weight into two components. But F and N are already perpendicular, so don't resolve them into components. Now, from the non-inertial frame of the car is at rest or moving with uniform velocity. From the car's frame, non-inertial frame, the rider of the car will say that I am not skidding outside, I am not falling inside, I am not lifting above the incline, I am not going inside the incline. So what is the net force on my body? 0. So he will balance all the net force. Along the incline, there is no motion, so net force along the incline should be 0. So just equate F plus mg sin theta, that is equal to mv square by r cos theta. That is the balancing of the net force along incline. F plus mg sin theta equal to mv square by r cos theta. Now perpendicular to the incline net force will also balance, because car has neither motion in perpendicular direction also. Car cannot fly away from the incline. So net force along the perpendicular to the incline will also balance. So in that case you can write N equal to mv square by r sin theta plus mg cos theta. There are two forces perpendicular to the incline downward, that is N should be equal to mv square by r sin theta plus mg cos theta. Now we have the relation between friction and normal reaction, that is F equal to mu N. Write it, F equal to mu N, and then substitute the values. In place of F you have to write mv square by r cos theta minus mg sin theta. Write it. Just put the value of F, mv square by r cos theta minus mg sin theta. Now on that side put the value of N and calculate for V. Putting the value of F and N, you have to solve to find the value of V, such that we can say what is the maximum velocity with which the car can take the turn. Because even in banked road, if the driver is negotiating the turn with a very high speed, greater than the safe speed limit, then definitely it will skid. So this is coming mv square by r cos theta minus mg sin theta, that is equal to mu mv square by r sin theta plus mu mg cos theta. Okay, I put the value of F here and value of N here, multiplying with mu, so it will be mu mv square by r sin theta plus mu mg cos theta. Okay, now collect all the term having v square on one side. Suppose on the left side I collect all the terms, so it will be mv square by r common from both of them. It will be cos theta minus mu sin theta. Take all the terms having v square on the left side, then you can take mv square by r common, then it can be written as cos theta minus mu sin theta. Similarly, the other term mg sin theta is taken on that side, so from that I can take mg common, and can write it is sin theta plus mu cos theta. Done? This one is coming on that side, mg into sin theta plus mu cos theta. Okay. Now you can cancel one m and write this one as v square equal to rg into sin theta plus mu cos theta divided by cos theta minus mu sin theta. Dividing this one, you can write this v square equal to rg into sin theta plus mu cos theta divided by cos theta minus mu sin theta. Okay. Now can I write numerator by cos theta and denominator also by cos theta? Then this equation will become v equal to rg into tan theta plus mu divided by 1 minus mu tan theta. So this is the value of the maximum velocity with which the driver which a car can negotiate a turn in a banked road having angle of banking theta and coefficient of friction mu. Because friction is there, so coefficient of friction will be present to stop the movement. Banking is there, means one component of normal reaction will also help, a part of the normal reaction will also help for stopping the movement. Here it is coming that mg's component is coming with F to prevent the sliding, prevent the skidding. One component of mg will help friction to stop the centrifugal force effect such that the car cannot skid. So there are two components, one is friction, another is component of mg. Both are helping to stop or balance the centrifugal force such that the car will not skid when negotiating the turn with a high speed. Done? Now this one is the maximum speed. Now what is the minimum speed? In that case, in the maximum speed skidding will be there. If there is a minimum speed, there will be a slipping in this direction. So to prevent slipping, friction will be in the opposite direction. So don't solve the entire problem by taking friction in this direction. What changes? Only friction force changes the direction. So just in this equation replace mu by minus mu and you will get your answer. Replace mu by minus mu means friction changing the direction. If friction is mu n, if mu n is here, then if I replace mu by minus mu, then it will be minus mu n in that direction. That is the case for slipping. Skidding means it has a tendency to go this side. That's why I am considering friction here. Now for minimum velocity, there will be a slipping and in slipping case it will be in the friction will be opposite. So just write here for V minimum it will be root over of Rg into tan theta minus mu divided by 1 plus mu tan theta. That is the answer. So you have to remember this too, otherwise you have to draw entire free body diagram to solve. Now for the banked road for car and train etc., minimum speed limit is not required, because even if they can at rest at that the banked portion, they will not slip. But it is required for a biker who is in the death well race, circus death well race. So he is moving like this. So if he is exceeding a speed limit, he has a tendency to skid outside. And if he is not maintaining a proper speed and his speed is lower than that, it will fall, slip. So both the ways the speed limit is required. Okay, but for train and other thing, cars and etc., only the maximum limit required, minimum limit is not required at all. Okay. So this is the banking of the road problem, and this is an important topic. Many one question will definitely come from this topic. Three cases that we discussed. First one, in a road having friction but it is horizontal, cyclist is taking a turn perpendicularly. Next one, frictionless, cyclist cannot take the turn in perpendicular position, he has to tilt itself with respect to the vertical line such that he can take a turn. Third one, for the multi-wheeler, more than two-wheeler, then the problem is it cannot tilt, so only road has friction, and apart from that, if it is road is curved, then there is an additional component of weight comes to help the friction to prevent centrifugal force, and it can take the turn properly with this set velocity limit. Okay, so this is the entire banking of road problem. Now we are almost at the end of the motion of a mechanics of a single particle. Single particle motion is almost completed. Only one thing we will discuss from the two particle system, that is the collision problem. Rest of the thing of the system of particle, that is center of mass calculation and all other rest of the topics, next 5 to 6 chapters we will discuss when I will come back here on 23rd of August again for 1 week. In that time we will discuss the motion of the system, starting from the motion of the system of particle. I will try to complete up to the before heat. So whatever be the portions, motion of the system of particle is there, rigid body dynamics is there, gravitation, fluid mechanics and elasticity, viscosity, surface tension, all those things can be completed in that time. Okay. So we will discuss only the particles, two particle motion, two particle collision here, because once we completed the work power energy concept and we have already studied the Newton's third law of motion, this can be discussed here, though it's actually a part of this motion of system of particle, but still we can discuss it now because the necessary physical topics is already discussed. First, why Newton's third law is important? Does it only important because of the fact that it is telling if there is some action force, there is an equal and opposite reaction on the other body, or there is some other physical insight in the law? And like first law and second law, which are always true in classical mechanics. Classical mechanics means Newton's laws are valid in classical domain. Classical domain means very low velocity. If the velocity is comparable to the velocity of light, Newton's laws will not work. If the size of the particle is a subatomic particle like electron, proton, like this, in that case Newton's laws of mechanics will not work. So in these two domains there are corrections. In the first case, when speed of the particle is close to the speed of light, the correction is called relativistic mechanics done by Einstein. And in the subatomic domain, Newton's, for the motion of electron, proton, etc., Newton's law cannot give us proper answer. In that domain, the branch is called quantum mechanics, which was established by many people, including Einstein. Many people. Max Planck was there, Born was there, Max Born, and then Heisenberg, Schrödinger, many. Though Einstein in his later life believed that quantum mechanics is not a complete science, but he was one of the founder of the initial concepts of the quantum mechanics. Now, we consider only Newton's third law, and in all the domain of classical mechanics means large mass particle and very low velocity particle compared to the speed of light. In this domain called the classical domain, Newton's first law is true, Newton's second law is also completely true. There is no such exception to this law. Go to the other domain, subatomic particle, high velocity particle, then this will fail, second law will fall, but at least in classical domain it will not fall. But third law, remember, it's a very notorious law, because in some cases this third law is valid even in classical domain, and there are some cases where third law is not valid. Means you can consider that there are two particles, action and reactions are according to Newton's law mentioned as equal and opposite. So their direction should be like this. It may happen that first particle exert a action on this one, this is along this direction. Second, this particle exert a reaction on this one, that is like this, they are perpendicular to each other. This situation may also arise. Force may be equal in magnitude, but the directions are opposite. In case of a moving charge, we got this problem. If the two charges are moving, one along x-axis, another along x-axis and y-axis, then if I calculate the magnetic force on these two, you will find that one charge will feel force along this direction, another charge will face force along this direction, and in that case these two are perpendicular, so it is violating Newton's third law. For those forces only third law is true, and third law is not true for dissipative forces like viscosity or magnetic force in general. You can say that third law is true completely for conservative forces like gravitation force, like electrostatic force, like Hooke's law, spring force. All these cases third law is completely true. For tension and all these things you can say it is true. But if there is magnetic force, like velocity dependent forces comes, friction, resistance, viscous force comes, the magnetic force comes, both depend on velocity. and in that case Newton's law will not, third law will not work. Okay. Now we will consider that we are completely under the domain of the conservative force. We will not discuss those forces and those critical situations right now. Now we consider if there are two objects, one is there, other is moving. Okay, fine. So I consider two objects of mass m1 and this is of mass m2. I consider both of them are moving along the same direction. So no need to take vectors. m1, m2. No need to take the vectors because the direction is already specified along the x-axis, one dimensional motion. Now if I consider u1 is greater than u2, then there will be a collision. If u1 greater than u2 is assumed, then there will be a collision. And after collision what happens? During collision what happens? During collision, this is m1, this is m2, they are in contact. So m1 is exerting a force on m2, that is say F12, means force exerted by 1 on 2. So in turn m2 will exert reaction force, that is F21, and according to Newton's law, third law, we know that F21 equal to minus of F12. Minus of F12. Clear? Now after collision what happens? Many things can happen after collision, but first I will consider both the masses will be separated again and move with different velocities, but all along same direction. So I consider after collision this mass m1 is moving in this direction with velocity v1 and this mass is moving in this direction with velocity v2. Clear? Okay, for the time being I put the arrowhead over these velocities. Now when the particles collide, they are in contact for certain time, very small, let that time be t second. Write down. Let us consider that during collision the particles are in contact for t second. Particles are in contact for t second. Now force is applied only for this t second, right? After that if the contact loses, force is not there because they are colliding, means this force is contact force. So if there is no contact, then this force will not act. So force acts on the particle only for 3 seconds. Now only for t second. Okay. Now is this force a continuous force or it's a impulsive force? Impulsive force. And what is the difference between the impulsive force? Impulsive force will not produce a measurable acceleration. Okay. Due to normal forces, if there is a velocity at this point, the velocity will suddenly slowly increase and after certain time it will reach to this value. It is under the action of a constant force. But impulsive force means when the force acts, velocity jumps off and again fixed. It is not impulsive. Non-impulsive force is like this, velocity increasing like this, And impulsive force means jump and move. Can you give one example? Very common example. Okay, suppose if I applying a force on his body, suppose, okay, very slowly, suppose on his head, very slowly. So one time will come, he will shout in pain, too much pain will be there in these muscles and all these things. So slowly he will shout, and as I am applying more and more force continuously, he will shout more. Okay, so this is the force that is acting continuously. This is not an impulsive force. And let us consider the situation. He is there, I am not applying a constant force over a long period of time. Suddenly I slapped with a huge force. What will happen? Suddenly he got shocked. Why has sir beaten me? I am not doing anything. And after some time he will shout. So that is, initially impulsive force is there. The system is, all of a sudden it is an awkward situation to the system. Momentarily it jumps to a certain velocity and again fixed. So that situation is the between constant force and impulsive force. Constant force will continuously change the velocity, but impulsive force will change it all of a sudden and then fixed, as if nothing is going here. So this is the difference between constant force and impulsive force. Now, see, here this impulsive force acts, but whatever be the force, it may be impulsive force, maybe constant force, maybe non-contact force, maybe contact force, Newton's second law should be obeyed. Means force equal to rate of change of linear momentum. Force equal to rate of change of linear momentum. Now you tell me, this force F21 acts on which body? Body 1. It is given by body 2. So it is acting on body 1. So it will change the linear momentum of body 1, because we know only the force which acts on the body, it can change the momentum of that body. Who is giving that force, his momentum is not affected by this force. If I am applying a force on you, your momentum is changed. Due to this force, my momentum will not change. My momentum, if changes, that force comes from you on me. Clear? So here body 2 exerts a force on M1, that is F21. So it can change the momentum of body 2. So what is the second body's momentum? I can write the change. M2V2 minus M2U2. Second body's initial velocity U2. Sorry, first body. No? This one is acting on first body, so 1. Okay. So this force is acting on body 1. So change in momentum of body 1. That is M1V1 is the final momentum. M1U1 is the final initial momentum. So change in momentum will be M1V1 minus M1U1. At that change in momentum occurs in how much time? T time, in which the force acts. So this is this force. Change in momentum by time, that is the rate of change of momentum. That is called the force. So the value of the force F21 can be measured by M1V1 minus M1U1 divided by T, because this force changes the momentum of body 1. Clear? Now, the other force F12, it acts on which body? It's a reaction, so it's act on body 2. So it will change whose momentum? Body 2's momentum. So what is the second body's momentum? m2 v2 minus m2 u2. So write it, minus symbol, don't forget. So write this one, m2 v2 minus m2 u2 by t. This one. Done. So this is from the Newton's second law, that is change in momentum, mv minus mu by t, that is force. Now cancel this t and write it by opening the bracket on that side, m1 v1 minus m1 u1, that is coming minus m2 v2 plus m2 u2. Now collect all the term containing v on the left side and all the term containing u on right side. What you will get? See this one, m1 v1 plus m2 v2, this is equal to m1 u1 plus m2 u2. This is called, this last line is called conservation of linear momentum. And necessary condition is that external force should be zero on the two particle system. See, this is a two particle system. Which force I consider? Action and reaction only. So if these two particles together is constituting a system, then is there any external force? No. A part of the system exert force on the other, a part exert force on the other. That is internal forces. For the entire system, if you consider two particle system, then these two forces are internal forces. There is no outsider which can exert the force on this system. So external force is zero. External force zero means linear momentum of the system will remain constant. Sum of the linear momentum will remain constant. Means that for each part of the system momentum can change. But when you consider the total change of momentum for the entire system, it will not change, both in magnitude and direction. Suppose m1 u1 initially has 12 unit, this one is 8 unit. Then it may happen that after collision it may be 7 and this may be 13, such that the sum will remain. But for individual, is the momentum conserved? No. But for together, for the entire system, sum of the momentum is conserved. Clear? So that is the main essence of the third law, conservation of linear momentum. See, force can be impulsive. Even if we do not know the character of the force or cannot write force as a mathematical form, but still in that case the simple relation is obeyed if Newton's third law is valid. Conservation of linear momentum means what is happening at the time of collision, we can completely forget that and write the relation between velocities or momentum before collision and momentum after collision. What is going during the impulsive collision, that is completely eliminated. That is the main essence of the third law. Clear? Without knowing force, without knowing acceleration, anything, you can find a relation between velocities of the particle before collision and velocities of the particle after collision. So write down conservation of linear momentum only true if external force on the system is 0. External force on the system is 0. Internal force can be there, but that will not do anything. Now we will use this law to solve the first collision problem. Okay, check. And there are many problems also directly comes from this. The problems that I have given to you, and that some bomb explodes. Bomb explodes and it is two part, it's fragmented and moving into opposite directions. If the mass of the two part is given and one's velocity is given, you have to find the velocity of the other part. This type of problem is solved by conservation of linear momentum. So first I will give that type of a problem and then we will discuss the elastic collision. First write down. A bomb of mass capital M, a bomb of mass capital M explodes into three pieces. Okay, two pieces of equal mass. Two pieces of equal mass moves perpendicular to each other. In horizontal plane. Two pieces of equal mass moves perpendicular to each other in horizontal plane. What is the magnitude and direction of the velocity of the third piece? What is the magnitude and direction of the velocity of the third piece? Ratio of the pieces are 1:1:3. Ratio of the pieces are 1:1:3. See how to solve this problem. Don't consider gravity in this problem and say that masses are moving in projectile or moving upward. It is in horizontal plane, no gravity. See, now let us consider this explodes from this point. One mass is moving in x-axis, another mass is moving in y-axis. Okay. So masses are distributed in the ratio 1:1:. So I can consider this mass is m, this mass is m. Okay. Now this mass is moving along x-axis and this mass is moving along y-axis with same speed. Let us consider its speed is v I cap. Its speed is, due to speed is v, it will be, momentum will be mv j cap. It is mv I cap, it is mv j cap. Now what will be the resultant of these two momentum? Something. Now we consider third part is moving anywhere. moving anywhere. So what will be the mass of the third part? 3m. And suppose that is moving with velocity v3. That is moving with velocity v3. So according to conservation of linear momentum, for 3 particles I can write m1 v1 vector plus m2 v2 vector plus m3 v3 vector, that will be equal to m1 u1 plus m2 u2 plus m3 u3. But before explosion all the masses are together and it is at, so what is m1 u1 plus m2 u2 plus m3 u3? 0. So before explosion all the system is at rest, so every part has a velocity 0. So all m1 u1 m2 u2 m3 u3 are 0. This one, then write this one. What is m1? M. v1 is v. So m1 is m, v1 is v I cap. Then second one is m v j cap. Third one is m3. m3 means 3m v3 equal to 0. Okay. Now you have to find the value of v3 only. So I can write this one as v3 equal to v by 3 I cap plus j cap with a minus sign. Check. Calculate. Can I write this one? This mv I cap is taken on the right side, mv j cap is taken on the right side. Then taking mv common, I can cancel one m from both sides. Then divided by 3, it will be v3 equal to minus v by 3 I cap plus j cap. So this is the velocity vector of the third mass. What you have to calculate? Magnitude of this velocity and direction. So find the magnitude of this velocity. Root 2 v by 3, because it is coming as a vector, x component and y component are there only. Then I can write that magnitude of v3 will be root over of minus v by 3 whole square plus minus v by 3 whole square. So it will be root 2v by 3. This is the magnitude. See, what is the coefficient of I cap here? Minus v by 3. Coefficient of j cap is also minus v by 3, but I and j are perpendicular to each other. So this total magnitude will be root 2 times v by 3. And what will be its direction? 45 degree. Because see, I cap and j cap means x component and y component are equal. So this one will be along this direction, making an angle 45 degree with each axis. Because sum of the 3 momentum is 0, means if you calculate the sum of this vector and this vector, third vector should be equal and opposite to that. So sum of these two vectors must be here. So third vector must be this one is P3. So thrust vector must be along this direction to cancel the effect of the other two, such that the sum will remain 0. Before explosion 0, after explosion it should be 0. So if two are going perpendicular to this, third vector must be in the equal and opposite to that, such that the sum will again 0. You cannot see. See this portion P3. Acha, one or two of you come and write it from here and then distribute the others. Or one or two more come in front. Write this one, because none of the markers are refilled properly. Okay, so we are utilizing the concept of the conservation of linear momentum. Before explosion there will be no velocity, that's why entire linear momentum before explosion is 0. After explosion, linear momentum of different masses can be calculated by m1 v1 plus m2 v2 plus m3 v3, but whatever be, since there is no external force, it will be 0. So sum of m1 v1 plus m2 v2 plus m3 v3 should be 0. Now m1 v1, that is mv, m2 v2, its magnitude is also mv, but their directions are different. Then for the third part I calculate, because third part m3 has a mass 3m, because mass is given in the ratio 1:1:3. So v3 in a vector form comes minus v by 3 I cap plus j cap. So we cannot use any other thing other than the conservation of linear momentum, because it is a very useful problem. Now one question that will come from this side, this part also, write down. Most of the time you know one question, that is, whenever a bullet is fired from a gun, the gun will recoil. Why it recoils? Because of the conservation of linear momentum. Because if we consider the mass of the bullet is small m and it is moving with a velocity v1, and mass of the gun is capital M, it is moving back with velocity v2, then capital M v2 will be equal to small m v1 with a minus sign. That means we can say gun is there having mass capital M, bullet is there fired and it is coming with velocity v1, its mass is m, gun's mass is m. So I can write that final momentum is m1 v1 for bullet, final momentum is m v2 for gun, and initially before firing there will be nothing. Initially before firing all the system, bullet, gun, all are at rest, so net momentum is 0. Then we can write that velocity of the gun v2, this will be equal to minus m by capital M into v1, right? Small m by capital M, mass cannot be negative, so v1 if along this direction, means bullet is along this direction, then gun's velocity will be minus of v1, means in the opposite direction. That is called the recoiling. Okay, and gun is heavier, since its mass is in the denominator, so this velocity will be very small. So with which velocity bullet goes, gun will move back with a very little bit of velocity, because bullet mass is small but gun is heavier. Okay. Now similar to this one, another problem is coming, this may come in NEET exam also. This is very just like one liner MCQ, but student may be confused in finding the answer. Write down. I will give you the options also. A boat is floating in still water. A boat is floating in still water near a river bank. Near a river bank. Okay. A man is standing on the rearer end of the boat from the bank. Man is standing on the rear end of the boat. Man is standing on the rear end of the boat. Means in the opposite side, which is far away from the bank. Suddenly, the man starts to move with uniform velocity. Suddenly, the man starts to move with uniform velocity, and after some time comes to the near end of the boat. Comes to the near end of the boat. What will be the displacement of this boat? What will be the displacement of the boat? Okay. Achha. Mass of the man, small m. Mass of the boat, capital M. And length of the boat, capital L. Length of the boat, capital L. Now I am giving you the options. Question, repeat. Okay. How much you have written? After some time, man reaches the near end. Reaches the near end. Okay. Mass of the boat, capital M. Mass of the man, small m. Length of the boat, capital L. Find the displacement of the boat. See. The situation I will draw. This is the boat. This is the, suppose the floating. This is the bank. The man is here. He is walking with constant velocity. Its mass is m. Mass of the boat is capital M. And this entire length is given L. He is moving towards the other end. Option A. It is M L by capital M towards bank. B ML by M plus M towards bank. C ML by M plus M opposite to bank. D ML by M ML by M towards bank. Which one is correct option? Why m plus n? Which one is the correct option? It is similar to the recoiling problem. So recoiling means the boat will move in opposite direction, so away from the bank. So already two options are there which are showing opposite to the bank it is moving, option B and option C. Then among these two, which one is the correct? Near the bank it cannot move because man is moving near the bank. So due to recoiling, boat will move in opposite direction. Then opposite direction movement is given in option B and in option C. Then which one? Option? Oh, sorry. Towards the bank, এটা হবে towards the bank দিয়েছি না? আচ্ছা। First one is towards bank, second one, just a minute. Towards bank, এটা opposite হবে। হ্যাঁ। This one. First towards bank, second toward opposite to the bank. Which one is correct? See, already opposite to the bank, that is confirmed because recoiling means an opposite direction. Then already first two option you cannot consider as a valid option. Now between C and D, which one? Why C? Why not D? If it is a firing of bullet, which one you consider? The D. Why you are not considering now D? Why you are saying C? Man is on the boat, bullet is leaving the gun. After firing, bullet will leave the gun. The man, when comes to this end, man is not outside the boat, he is still on the boat. So when the boat moves back, he moves back with the man on the boat. So total mass will be there for the calculation of the momentum of the boat. While in the previous problem, for the calculation of the momentum of the gun, I have taken only capital M. But here I cannot take only the mass of the boat because the man is on the boat still now. So this is only difference from the previous problem. Rest of the part is same, conservation of momentum. So you have to remember this one, whether the mass which is fired or anything having velocity, whether it is leaving the system or it will still in the system and the entire system is moving back. Here the entire system, boat with man, is moving back. So there will be both the masses in the denominator. But in the firing of bullet, there is only mass of the gun in the denominator. Okay? So particle motion is almost complete, particle dynamics. Now see, Now if we are considering that two masses are there, one is m1, another is m2, moving with velocity u1, moving with velocity u2, and we consider u1 greater than u2, they will collide at this moment, and after collision they are again separated from each other and moving with velocity v1, and this one is moving with velocity v2. Then I can write conservation of linear momentum for them, because collision produces only impulsive forces, there is no external forces from any other third agent. So I can write conservation of linear momentum, and since it is one dimensional, I can drop the vector sign and simply write m1 v1 plus m2 v2 will be equal to m1 u1 plus m2 u2. Conservation of linear momentum. But now I haven't put the vector sign, because I consider the collision is taking place in one dimension. So this is my first equation. Now in a typical collision problem, there are two unknown quantities, final velocity and both the final velocity, not the initial velocities. Final velocities are v1 and v2, and m1, m2, u1, u2, all these quantities are given to you. It is specified. Then you have to calculate v1 and v2. Can we calculate v1, v2? If masses are given and velocities are given, u1, u2, m1, m2, these four quantities are given, can we find v1, v2 from this? Not possible, because unknown are 2, equation given 1. So how can we solve? We need a second equation. How the second equation will come? Conservation of momentum will give us one equation. How the second equation will come? Yes? Conservation of kinetic energy. But see, this kinetic energy, it is very notorious. It is not a very good student like momentum. If external force is 0, linear momentum is always conserved. So you can write this conservation of linear momentum for any type of collision. There are many types of collision called the elastic collision, inelastic collision, partial elastic collision, collision in two dimension, in any type of collision, or even explosion problem, in even scattering problem. All this linear momentum is a very good student and it is always conserved. Only thing is that there will be no external effect on that, no external force should be given, then linear momentum is always conserved. So you can write this equation for any collision problem. But kinetic energy is not that much. Kinetic energy can change even if there is no external force. In a particular case of collision called the perfectly elastic collision, kinetic energy will remain conserved. Okay, so the first case, write down perfectly elastic collision. Perfectly elastic collision in one dimension. So that we are going to discuss. We get conservation of kinetic energy also, and since we considered this one, then we can write here half m1 v1 square plus half m2 v2 square equal to half m1 u1 square plus half m2 u2 square. This is my second equation. Okay, but remember, only perfectly elastic collision. In that case you can write the second equation. Now how many unknowns? 2. How many equations? 2. So we can solve to find the values of V1 and V2. Okay, but see, still we are having some problem. Problem is that first equation is linear. Okay, fine. Second equation is quadratic in V1 and V2, and it is always difficult to solve the quadratic equations. One equation linear, another equation quadratic. Then you are facing problem. So many extraneous roots can come. You have to cancel all these things all. But if I have one more linear equation which doesn't contain any square or anything, then it will be more advantageous to us. We can solve it easily. So we are searching for another linear equation. But is there any other conservation principle of physics to give us another linear equation? I cannot make a linear equation out of no physical law, because physics is related to the physical law, and only physical law can permit us to write the equations. I write two equations by using two physical law. One is conservation of linear momentum, another is conservation of kinetic energy. There is no other such conservation law like physical law or anything which give us a third equation, which I claim to be linear. Then the problem is, how can we find? Whatever we have to find a linear equation, I have to find out of these two. By manipulating these two, I have to prepare a third equation, because I don't have any other law to use here. Okay. Now, this is just a part of mathematics to prepare one more linear equation. I can write equation 1 in this manner. M1 common, V1 minus U1. M1 common, V1 minus U1, right? Taking this term on this side, I take V1, M1 common. Similarly, I will take this term on that side and take M2 common accordingly. I write U2 minus V2. This is my, say, third equation. From 1 it is prepared. Then from the second equation I can do the same thing. First of all, I will cancel this half. All the term containing half. So half can be cancelled. Now from the second equation, can we write this one taking M1 common? It will be V1 square minus U1 square. V1 square minus U1 square can be written as V1 plus U1 into V1 minus U1, that is A square minus B square, that is A plus B into A minus B. So can I write A minus B in front? I can of course write that. So it will be V1 minus U1 into V1 plus U1. After this term M1 taking common, I got V1 square minus U1 square. Then I split it into A plus B into A minus B formula. That is V1 minus U1 into V1 plus U1. Okay. So I will do the same thing on the right side. this term is taken on that side, m2 common, then you will get u2 minus v2. So it can u2 square minus v2 square, which can be written as u2 minus v2 into u2 plus v2. Done. This is your equation, suppose 4. Now divide equation 4 by equation 3. Divide equation 4 by equation 3, both side. Divide it and tell me what you get. Equation 4 divided by equation 3. Many things will cancel from both sides. Yes, you are getting V1 plus U1 equal to U2 plus V2. Now you write this one in this format. V2 minus V1 equal to U1 minus U2. Equation 5. V2 minus V1 equal to U1 minus U2. This one is a physical equation related to the one-dimensional elastic collision problem. See, suppose you are sitting on the mass m2. You are sitting on the mass m2 and this mass is moving to collide with you. Someone is throwing this stone to collide with you. You are looking towards this mass, seeing this one, and you are at rest, suppose, means u2 will be 0. So with how much velocity it is coming towards you? u1. But if it is moving, you are moving in this direction with velocity u1, then this mass will collide with you after some more time, because you are already moving away. So what is the velocity of this mass now with respect to you? u1 minus u2, that is called the relative velocity. If you are at rest, you will feel that this mass is coming with a velocity u1. If you are moving, you will say that this mass is coming to me now with velocity u1 minus u2, because time is increased, means you will feel that the velocity will decrease. That is called the relative velocity. Now this is the relative velocity of approaching of the mass to collide with you. Then during the collision, both of you are in contact. After collision, what you feel? That this mass is moving away from you. Gap is again separating. Gap is now separating. So this mass is moving away from you. So now V2 minus V1 will be the relative velocity of separation. So this equation shows that in one-dimensional elastic collision, perfectly elastic collision, relative velocity of separation is equal to relative velocity of approach. So write down relative velocity of separation equal to relative velocity of approach. This is only valid in one-dimensional perfectly elastic collision. Now we have equation 1 linear, equation 3, equation 5 linear. Then we can solve to find V1 and V2 easily. No quadratic equation will come. Clear? This is 1, this is 5. 1 and 5, there is no square term, so we can solve it easily by using any simultaneous equation solve. But if you try to solve directly 1 and 2, it is difficult, because there is square and many terms will come. after squaring on all these things. So this is, after this there is just the solution, find the value of V1 and V2, and then some cases are there, those we will discuss later. Directly interchange the velocities of the, if the masses are equal, then it is directly interchange. Interchange means that part should be same. So equal transfer occurs only when masses are same. If the masses are not same, that is a special case when I will consider M1 M2. Okay.